Okay, so I don't know who's supposed to be right. Does anyone want to put a solution on the board and have us do it? Each of them? No?
Is it for the homework today? Or?
Yes, for the homework today. Okay, well, let's get started then. Let's not waste any more time. So there, we were talking about basic sort of building blocks of limits. So basic limits that you've probably seen before, but not seen proven. So the limit of 1 over n to the p for any p bigger than 0 as n goes to infinity is going to be 0. 2, the limit of a to the n if the absolute value of a is less than 1. The limit of a to the n is 0 as n goes to infinity. 3, this is the sort of cool one. The limit of n to the 1 over n as n goes to infinity is 1. Right? If you take 3, the cube root of 3, the fourth root of 4, the fifth root of 5, etc., it goes down to 1. Number 4, the limit of a to the 1 over n as n goes to infinity is also 1 for any a bigger than 0. This is probably one you saw as a kid, playing with a calculator. If you took successive roots of any number, even if it was smaller than 1 or bigger than 1, you're going to end up at 1 anyway. If you took successive square roots. Okay. So this one, you remember we did using the binomial theorem, right? We used, to recall that in number 2, we used the binomial theorem, and we said, well, look, if you have 1 plus b to the n, right? What's 1 plus b to the n? Well, it's going to be 1 plus b to the n plus some number of b to the n's plus some number of b to the n minus 1 plus some number of whoops, let me get this right. It's going to be 1 plus some number of b's plus some number of b squareds plus some number of b cubes plus dot 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 plus some number of b to the n. Right. Right. And where do these numbers come from? Pascal's triangle, right? They comes from Pascal's triangle, right? Or you can think of them as the choose, right? This is going to be n choose n, right? This is n choose n minus 1, n choose n minus 2, and so on and so forth, right? Down to n choose 0, and then so okay. So we're going to use that. I'm sorry, I got it wrong. So this is n choose n, n choose n, n choose n minus 1, n choose n minus 2, and so on and so forth. Right, and so it ends up being like 1 plus nb plus n minus 1 over 2 b squared plus etc. etc. Okay. So anyway, we're gonna use this again in the proof of number 3. So proof of 3. So we want to show that the limit is 1. In other words, given any epsilon, oh, actually, I'm just going to write it this way. So we want to show that the limit of n to 1 to n. So here's the trick we're going to play. Let x of n be n to the 1 over n minus 1. Okay, so it's a distance from this between this thing and the limit, and it's positive. Notice that it's positive. And so it suffices to show that the limit of this guy is 0. Okay, so what we're going to do is try to use the binomial theorem to say something about this. Say something about x of n. Okay, so we say, well, look. Well, we see that 1 plus x of n, quantity to the n, is n. Okay, so I'm going to write out 1 plus x of n to the n, that's equal to n. And we're going to pull something out of the binomial theorem. We'll say, well, this is bounded below by n times n minus 1 over 2 x of n squared. Okay. Right? Because 1 plus x of n to the n is this whole polynomial here. So that's certainly bigger than just one of the terms. Okay, so we just pull out one of the terms and say that's our lower bound. Ichan, are you okay?
Yeah, I'm just wondering why does 1 plus x n to n equals n?
We made it that way. X of n.
Sorry.
Wait, we made it that way. X of n is n to the 1 over n minus 1. You move the 1 to the other side and take the nth power. Right. Okay. So so what do you see? That tells you that x of n squared is less than n times 2 over n minus 1. Right. So taking the square root of both sides, taking the square root of both sides, we get that x of n is less than the square root of 2 over n minus 1. Is it okay to take the square root of both sides? Why can we take the square root of both sides? If you have some inequality, a is less than b, does that tell you that the square root of a is less than the square root of b? Well, they have to be positive to take the square root.
So that's a condition.
So it's okay. So it's okay. The point is that what's the reasoning? The thing is that the square root is an increasing function, right? Increasing function means that if you have something that's less than something, then the outputs are going to be less. The corresponding outputs are going to have the same relation. Okay. So the one that we used earlier was this one. If you have the square function. If you have the square function, then it's okay to do this, but only if you have dealing with positive numbers. Okay, because only if it's positive is it an increasing function. Okay, so you need to stick to the part where it's increasing, and then it's okay. Any questions? Okay, So what's good about this? What can you do with this? What does this do for us? X of n is less than the square root of 2. Amy?
By part 1, the square root of 2 over n minus 1 is 0.
Yeah. Yeah. So by part 1, we know that the thing inside the square root is going to go to 0, right?
So could you take the limit of both sides?
Yeah. So, well, not exactly. What you do is, I mean, so here's what you have. We have something like this, right? X of n is bigger than x of n is positive, and it's bounded above by this, right? So you can use the squeeze theorem, say. Right? Take the limit of this. The limit of this is 0. The limit of this is 0. And then so that gives you that the limit of the inside guy is going to be 0. So by the squeeze theorem, we're done. Okay. Let me ask you a question. What happens if we didn't use, so we used the second term of the binomial theorem. What would have happened if we used instead, we tried to use this term? Would it still have worked? Suppose we say, instead of saying bounded below by this, we say, well, this is going to be bounded below by n times x of n. Then what would happen? Is that still okay? Still going to work? I see you, Ichan. Don't worry. I see you. Okay, Ichan, go ahead and say. What happens?
So xn is smaller than 1.
Xn is smaller than 1? Yeah.
And when you use the squeeze, you couldn't do anything.
Yeah, that's right. It won't tell you anything. Right. It won't tell you anything. Right. What about if we use the third term? What about if we use the third term? I think it'll work. I think it'll work if you use the third term. Because you'll use the cube root. You'll have some, you have some extra n on the bottom. You're taking the cube root of that, and it'll go to 0. Okay. Okay. Let's go on actually to to the last idea in this section, infinite limits. You have some sequence, and this. We want to talk about what it means for the limit of the sequence to be infinite as n goes to infinity. So maybe somebody knows the definition already. What does it mean for a sequence to go to infinity? How do we define this? Anyone? Can anyone say? No? Mia, go ahead.
Does it mean it's unbounded?
It's unbounded? Well, not just that it's unbounded, because an unbounded sequence could be something like this. Or something like it goes up and it comes down, it goes up and it comes down, it goes up. And this sequence is unbounded, but you don't say that it goes to infinity, right? So to go to infinity, it really has to sort of unidirectionally go to infinity. Right? So how do we make that happen? How do we make it so that it can't come down again?
Absolute value.
Say it again.
Absolute value.
No, because then if we're looking at the absolute, are you saying look at the absolute value of the sequence? If you
Never mind.
Okay, if you said look at the absolute value of the sequence, in that case you can have a sequence that goes like this, right? Positive, negative, positive, negative, positive, negative, and its absolute values would be, if you put absolute values on it, you don't see that it's oscillating. Right. Okay. Does anyone know? Anyone?
Lower bound.
Yeah. So you say, well, there's basically it's this idea of a bar, right? You say, given any bar, there's going to be some time past which it's over the bar. Okay. So if given any bar m, there exists a time such that if n is bigger than n, S of n is over the bar, then we say the limit of S of n is infinity. As n goes to infinity. Okay, so I'm going to do a simple one just to start you off. The limit of n squared plus 1 over n as n goes to infinity is infinity. Okay, so right. So you want to we'll do some scratch work as usual. Right. We want n squared plus 1 given n, we want this thing to be bigger than some n. Okay. And we want to know what condition implies this sort of thing. Okay, so this is a pretty simple one. Maybe you can't see it immediately. Maybe you don't see directly what the n has to be, but you say, well, look, n squared plus 1 over n is bigger than n squared over n. Right? N squared plus 1 is bigger than n squared. Right? So this thing is bigger than n. N squared plus 1 over n is bigger than n. Right? So if n is bigger than m, certainly n squared plus 1 over n is bigger than n. Right? Because this is bigger than n, and n would be bigger than n. And then, once you get that, then you write it down. You say, okay, so here's the proof. Given any n, let n just equal n. If n exceeds n, which equals m, we see if n exceeds n, then n squared plus 1 over n exceeds n which equals n. Right? So our terms are all over the bar. So past that point, our terms are all over the bar. Past that point, our sequence exceeds the end. Okay. Everyone all right? Yeah. Okay, so this is a simple one. Let's do another one. Just slightly more complicated. Okay. The limit of n squared plus 1 over n plus 2 equals infinity. So, do you want to try it? Why don't you try it? Okay, so given m, find an n such that if n exceeds n, this thing is bigger than n. Okay, and the game will be just like before, just like in the previous one. Try to find something that's smaller than this that you can make bigger than m. Okay. So find something like something that's smaller than this that you can make bigger than m if n exceeds n. Actually, let me give you the other part of it. So, and the way you want to think, of course, is that this n plus 2 is basically n, right? So this is, again, sort of the morally speaking argument. Morally speaking, n plus 2 is something like n, right? So try to ensure that try to find some condition to make it like n, and then use that. Okay, so this is the main trick. Okay, does anyone see what needs to be done? What do we need to do to pull off this trick successfully? The n plus 2 is like n. Can anyone see what sort of explain the idea? Right, we have n plus 1, n squared plus 1 over n plus 2, right? We want some sort of lower bound on this guy, right? We want some sort of lower bound. We would like to say this, right? We'd love to say that, because if we say that, we're in the same situation as in problem 1, example 1, right? So what do we need to, can we say that? Can we say that? Is it true that, to do that, we'd have to say that this is bigger than that, right? N would have to be bigger than n plus 2, right? Because if n is bigger than if n is bigger than n plus 2, then 1 over n plus 2 is greater than 1 over n, right? That would be great, right? But that's not true, right? N is not bigger than n plus 2, but what can we do here? We will just say, what we'll do is we'll say n plus 2, well, 2n is bigger than n plus 2, right? 2n is bigger than n plus 2 as long as n is bigger than 2. Right? As long as n is bigger than 2, we're good. Then this is true, right? And then we can say this is true. Okay, right? So then we have this, which is just as good as what we had before, because it doesn't really matter that we have this constant, right? It doesn't really matter that we have this constant. Right? This is going along the same lines as before. We'll say, well, this is bigger than n squared over 2n, right? So that's n over 2, right? So as long as n over 2 is bigger than n, then n squared plus 1 over n plus 2 is bigger than n. Right? And so we get our n condition, right? Our n condition is this one. Right? Our n condition is n needs to be bigger than 2m, and it also needs to be bigger than 2. Okay, so that's your scratch work, and then once you work out the scratch work, you write it out. Okay, here's the proof. Right, given m, take n to be the max of 2 and 2m. Or actually, let me just be safe, I'll say bigger than the max, so that I don't make any. Yeah, because I wanted n to be bigger than 2. It doesn't really matter. But anyway, being overcautious as usual. If I were my advisor, he'd probably say bigger than 10 to the 10 times the max. Yeah, and that would certainly avoid any troubles. Okay. But the point is that it doesn't matter, right? I can take any huge constant times this. It doesn't matter. Okay. Okay. Then, if n is bigger than that n, we see that n squared plus 1 over n plus 2 exceeds n squared plus 1 over 2n, since n plus 2 is less than 2n for n bigger than 2, right? And this is bigger than n over 2, right? Bigger than n over 2, right? And that is bigger than 2m over 2, right? Since n exceeds 2m. right? Which is n? If you want, this is because n squared plus 1 is bigger than n squared. Okay, so for all n bigger than that, our guys exceed the m bound, right? And that's the end. Okay, so again, this is an example of the sort of moral reasoning. Right? You say, well, this n plus 2 is basically an n, and then you try to ensure that it is an n. It is basically an n in the right way. Yeah,
For
John.
the second quotient to the third quotient, what happens to the denominator? 2n, from 2n to 2.
From here to here?
Yeah, the denominator.
Yeah, right, because we've got n squared on the top, and then 2n on the bottom, right? So we get n over 2. Okay. Last example. If r is bigger than 1, then the limit of r to the n as n goes to infinity is infinite. Okay. And the proof of this one is kind of cool. You say, well, let r be 1 plus h. Okay. 1 plus h, some small number, some small positive number h. Okay. And so we want to show, right, that the limit of 1 plus h to the n as n goes to infinity is infinite. Okay. Just to rephrase it. For any positive number h, it suffices to show that this thing is infinite. Okay. Okay. So what are we going to use? 1 plus h to the n. We're going to use the binomial theorem, right? Okay. So we know that 1 plus h to the n exceeds, for example, n times h. Right? By the binomial. Theorem. Okay. So then that'll basically do it for us. Given any n, choose n such that n times h exceeds n. Right? Because if nh exceeds m, then certainly 1 plus h to the n exceeds m. Right? Just to be pedantic, why can we do this? You have some positive number, you have some other positive number. How do you know that there's some natural number such that that natural number times one of them exceeds this? This is a theorem, actually. This is we proved it, right? This is the Archimedean property, right? So this is actually Archimedean property. You can do that because of the Archimedean property. You don't really need to say that. I think that's pretty obvious, but it's sort of cool to say that it actually comes from something we showed. Okay. So then if little n is past that big N, we see that, so I should, sorry. where r equals 1 plus h. Oh, we're ready. No. Then we see that you know, nh is bigger than nh is bigger than m, and we saw earlier, and by star 1 plus h to the n is bigger than nh, and so on. Yeah. I guess this is a little bit sloppily written. Normally I would start from here and then, you know, incorporate this stuff down below. But I already wrote it out, so I'm just going to use it. Yeah, bad writing. Bad writing. Okay. Okay. Everyone following? Okay. So theorems for infinite limits. Theorems for infinite limits. Say that you have a sequence a sub n that goes to infinity, and you have another sequence b sub n which is bounded below by some number k. Then a sub n plus b sub n diverges to infinity. Or you could say converges to infinity. Anyway, it goes to infinity. The limit of it is infinity. And 2, a sub n, b sub n goes to infinity as long as k is positive. And number 3, c a sub n goes to infinity for all positive c and goes to negative infinity for all negative c. Okay. Which one do you want to? I'll let you try one of them. Okay. Take 2 minutes and try one of them. Which one do you want to try? Number 1 or number 2? Just show that the sum diverges to infinity, or that the product goes to infinity. It doesn't matter. They're both almost the same. They're both around the same argument. How about the second one? Let's do the second one. Okay. Okay, there's not too much time, so let me just cut in. First off, about the first one, you have one sequence that goes to infinity, and then the other one is bounded below by some k, and the sum is going to go. Then the sum is going to also go to infinity. What if b sub n is not bounded below by some k? Then give me an example. Give me an example how this goes wrong. Okay.
Because if bn goes to negative infinity?
Yeah, bn goes to negative infinity, right? You say, suppose an is n, an equals n, and bn equals negative n. Say, right? Then this one goes to infinity, but the sum is 0 everywhere, right? Or you could take bn being negative 2n or something. Then the sum would go to negative infinity, right? Or you can make it go wherever you want, actually. Okay. So this one, I want to show. So proof. I want to show that given any n greater than 0, there exists an n such that if n exceeds n, then a sub n b sub n exceeds n. Right? So like, the only thing we have is that b sub n is bounded below. Right? So b sub n are all bounded below by some k, which is positive, and we know that a sub n goes to infinity. Right? A sub n goes to infinity. Right? So we can play the m-n game for the a sub n's, right? So what do we do? Does anyone know how to do it? Flo, you look like you know how to do it.
I have an idea.
Yeah, great.
That's what I would say first. So for a sub n, we know that for any n, there exists n greater than n.
Mm-hmm.
So that a sub n is greater than n.
Mm-hmm.
And then we say that since b sub n is positive always,
Mm-hmm.
then a sub n times b sub n will always be greater than a sub n.
Well, we don't know that a sub n, b sub n is always greater than a sub n, but we know that it's greater than, say, k a sub n.
Okay,
Yeah.
that makes
Right?
sense.
Because
K
b sub n is bigger than k. K is the positive number. Right? K, it could be less than 1. Right? In which case, a sub n, b sub n would not be greater than a sub n. Yeah. So, but yeah, that's the red line. That's the red line. So you say, okay, so just choose your a sub n so that we want this to be bigger than m. So what do? We choose the a sub n so that they're bigger than. I was going to hold my breath until somebody answered, but I think I'm going to die.
Will you say that again?
Yes. We want this. Remember, we're trying to make these guys bigger than m, right? We can make these guys as big as we want. How big do we need to make them to make this guy bigger than m? Me?
A sub n bigger than n.
A sub n needs to be. We want this thing to be bigger than m. Wait, this is what we want. So how big do the a sub n's have to be? M over k. Yeah. So since a sub n goes to infinity, there exists an n such that past that point, a sub n is bigger than m over k. So then, of course, a sub n, b sub n is bigger than a sub n k, which is bigger than m over k times k, which is n. And exceeding that n. So you use the So you use the n from your a sub n sequence corresponding to this bar, right? You're trying to get everybody over the m bar. You use the time corresponding to the m over k bar for a sub n. And you say, well, look, then for the product, everybody's over the m bar. Okay, that's it for today.